We are on the verge of a revolution in how we build virtual worlds. I mean, a genuine leap from the silicon limits of today's hardware to a future that's powered by quantum mechanics itself.
Think about it. Every single game you've ever played, no matter how big or amazing, it has a wall. You can't see it, but trust me, every developer on the planet feels it. It's this invisible barrier that dictates how big a city can be, how many characters can be on screen, how real the physics can feel. It's why even the most jam-packed game world starts to feel kinda, empty or fake if you look too closely.
And this number? This is what builds that wall, 16.67. This little number is the absolute tyrant of real-time graphics.
That's 16.67 milliseconds. It's the entire time budget you get to create one single frame if you want your game to run at a smooth 60 frames per second. And to hit that insane target, developers have to pull all sorts of tricks. They have to approximate, they have to fake it, and that creates visual noise, that smudgy-looking shadows or physics that feels a little off. This is what we call the silicon ceiling.
So how in the world do we break through that ceiling? What if we could build a bridge? A bridge to a totally new kind of computation, one that doesn't just approximate reality, but actually solves it. Well, this is exactly where the hybrid quantum model comes into play.
The key to this whole thing is NVIDIA's CUDA-Q. The best way to think about it is as the ultimate universal translator. It's this open-source platform that lets the classic CPUs, our powerhouse GPUs, and these new things called QPUs, quantum processing units, all speak the same language. It's literally the blueprint for this new hybrid bridge.
So here's how this new dream team works together. You've got the CPU, it's the conductor, right? It's orchestrating all the game's logic. Then you have the GPU, the workhorse rendering all those gorgeous visuals. And the QPU? The QPU is the specialist. It's the genius you bring in to solve the problems that are just flat out impossible for the other two. And this is how we talk to that specialist. It's called a quantum kernel. It's basically a piece of code that runs on the quantum hardware. But here's the mind-bending part. A GPU shader is like a painter, right? It's meticulously filling in a canvas, pixel by pixel, step by step. A quantum kernel, on the other hand, is like a sculptor who sees the final statue inside a block of marble and, in what feels like a single move, just removes everything that isn't the statue. It reveals the perfect solution instantly. It solves. It doesn't iterate. So when I say impossible problems, what am I actually talking about? Well, let's look at three of the biggest headaches in modern game development: lighting, physics, and AI. Okay, first up, lighting. The classic method you see on the left is kind of like trying to figure out the shape of a dark room by just randomly firing a paintball gun 16 times. I mean, you get a rough idea, but it's messy, it's noisy. The quantum method on the right, quantum amplitude estimation, is like having a sonar that pings the room just 4 times and gets back a perfect, complete map. It's not just faster, it's fundamentally smarter. You get a perfect result, which means visual noise could become a thing of the past.
Now let's talk physics. Picture a massive bridge collapsing into thousands of pieces. A classical physics solver on the left has to grind through it, calculating the forces between each piece, one by one, frame by frame. It struggles. But the quantum HHL algorithm on the right, it can see the entire puzzle all at once, every single piece of rubble and how it connects to every other piece, and it solves the entire system instantly, in a single quantum heartbeat.
And what about AI? This is where it gets really wild. Imagine you're trying to teach an AI to behave in complex ways. The classical AI on the left needs, say, 8,000 parameters to get a pretty basic result. The quantum AI on the right, using something called the variational quantum circuit, can produce exponentially more complex, more nuanced, and unpredictable behavior with just 24 parameters. How? Because each of those quantum parameters could hold way more information, allowing for this incredible richness from a tiny, tiny instruction set. Okay, so we've got these incredible new quantum tools, but when does it actually make sense to use them? When do we hit that tipping point, that moment where quantum just takes over? The answer is in the math. For problems like lighting, we get what's called a quadratic speedup. That's a huge deal, a massive improvement. But for those really complex systems, like our physics simulation, the speedup is exponential. And that is the absolute game changer. Look, a quadratic speedup is like going from a fast car to a supercar. An exponential speedup is like going from a fast car to a teleporter. It lets you do things that were fundamentally impossible before. And this is what that exponential leap actually looks like.
A problem that is computationally impossible for classical hardware. Something so hard it would take the age of the universe to solve. Doesn't just become possible for a QPU, it becomes trivial.
In that crossover point, it isn't just some technical milestone. It is the exact moment our entire idea of what's possible in a game world completely shatters. It's the moment we stop building clever fakes and start computing realities. This is how open-world games become infinite-world games.
And I want to be clear, this isn't just science fiction. This is a roadmap. The journey from the research we're doing today to the games you'll be playing tomorrow is already being mapped out.
Right now, we're in the very early days, the NISQ era, using our most powerful GPUs to simulate what these quantum computers can do. In the near term, we're going to see the first real, stable, fault-tolerant quantum hardware come online. In the future, the destination? An entire game engine built from the ground up to be quantum native, the infinite world engine.
So I'll just leave you with this question to think about. For decades, we have been getting better and better at simulating reality, at faking it, all inside that little 16.67 millisecond cage. What happens to our games, to our stories, our digital worlds, when the engine is finally powerful enough to stop faking it and just compute it?